We are now to the first law of thermodynamics, which is fairly important, but is actually not going to be a big step from where we have been up to this point. Previously, we had the energy principle, and we expanded the energy principle now to include both an external work and our heat. And so this is a change in our system energy. And what we can do is actually ignore macroscopic motion. So what does that mean if we're ignoring macroscopic motion? Well, that means that we don't have any change in mechanical energy. That all we're doing is zooming in on this part of the equation, which is in fact the first law of thermodynamics. And this is going to be the most important one that we're working with, especially for right now. So this is going to be that the change in thermal energy is equal to the work done plus the heat transferred. And again, we have sign conventions for both of these. We're now going to talk about the consequences for this and how we use this to further understand PV diagrams and the different ideal gas processes. This energy model now is a different energy model from what we were using before. We've added heat, so we now have work and heat, but we're really going to only think about thermodynamic properties. We're thinking about what's happening to these state variables. We're not worried about, for instance, potential energy. So thermal energy is going to be the primary property or only property of the system that we're really focused on, but we could then be connecting this with the ideal gas law, pressure, volume, temperature. So work and heat are going to be the transferred energy between the system and the environment. When we have positive work and positive heat, that's energy transferred in. When we have negative work and negative heat, that's energy transferred out from the system to the environment. And it's possible that you might have multiple things going on at once, such that you have to keep track of both of these, but then you could think about the net work and net heat. The first law of thermodynamics says that our change in thermal energy is going to be equal to the sum of these. So if we have energy added, they're both positive. If we have energy removed, they're negative. When I say both here, they can be changing independently. So if I have work in and heat out, if they're equal, that actually would tell me that one is positive, one is negative, and they cancel, such that delta E thermal is 0. And we'll be talking about that in the next few slides. So where this model fails is if we actually need to worry about mechanical energy of our system. If we're worried about kinetic energy, if we're worried about potential energy on that macroscopic scale, then you don't want to use this model. So thinking about our basic energy model, that's good for the motion of a ball. Thinking about our thermodynamic energy model, that's good for the state variables of an ideal gas. So now let's look at a few different processes and understand how we can think about them using the first law of thermodynamics. The first process we're going to think about is the isothermal process. Now the definition of this is that the temperature stays the same. That means that the change in thermal energy is 0. Again, we haven't quite related thermal energy to temperature yet, but trust me, it's basically proportional. So if the temperature has stayed the same, our change in thermal energy is 0. From the first law, we know that work plus Q must equal 0, where Q is heat. So what this means, we can rearrange to say that Q is the negative of work. Why is that interesting? Well, from the PV diagram of an isothermal process, we can integrate to find work. Right? Remember that from a PV diagram, we can do the negative integral and get the work. So what this means is you know from a PV diagram what the heat is for an isothermal process, but you would actually have to calculate the work to answer that. What this looks like then, if we look at a bar chart, and these bar charts are going to be looking at work and heat on the left side with our initial thermal energy, and then summing them up to get our final thermal energy. That in this case, when we have an isothermal process, we have work, but it's negative. We have heat, but it's positive. And obviously these could flip around depending on the direction that the isothermal process is going. But this means that since these cancel, our initial energies and our final thermal energies are the same. So this is important. This is one of the hallmarks of an isothermal process. The thermal energies are the same. Work is done, either positive or negative, and Q actually cancels that. So be careful. Just because the temperature is the same for the beginning and final states of an isothermal process, that does not mean that heat is zero. Heat must not be zero because heat must be canceling the work. This is a really interesting and important consequence of the first law of thermodynamics, and one that you can't really think through without the first law of thermodynamics. An isochoric process is different in that by definition, the work is zero. Why? The volume is zero. And remember that if the volume is zero, the integral is going to be zero because you get a vertical line in that PV diagram. So work is zero, which means from the first law that the change in thermal energy must just be equal to Q. So in this case, we haven't done any work on the system because the volume has not changed. So whatever our Q is our change in thermal energy. If we've added heat, we've increased our thermal energy. In this case, heat is negative. We've taken energy from our system to the environment, so our final thermal energy is less than our initial thermal energy. This would tell you that our final temperature is less than our initial temperature. The adiabatic process is, again, one that we'll talk about a little more later, but this is where it first shows up in the book. So the definition of an adiabatic process is where Q equals zero. Again, one way this can happen is that the process can be so fast that there's actually no time for heat to be transferred. And again, that might seem like it's in conflict with our quasi-static process, but it's actually not for the processes we talk about in this class. Another possibility is that you have a perfectly insulated system. That's again when you can't have any heat transferred. So there was a typo on the slide. Because the thermal energy is equal to work plus Q and Q is equal to zero, our change in thermal energy must be equal to the work done. So whatever thermal energy we have, the change in it, just equal to work. Q equaling zero is the definition of the adiabatic process. Remember that for an adiabatic process on a PV diagram, the pressure, volume, and temperature all change. So the volume changing tells you about work. The temperature changing tells you about this change in the initial and final thermal energy. But the pressure itself is also changing, and so knowing that Q is equal to zero is what defines the adiabatic process. Lastly, I want to run through a scenario where I use the first law of thermodynamics to actually analyze this. So there's a few questions that you want to ask, and it's helpful, at least in this case, to go in this order, though the order might vary depending on what you know. First, is this a special type of process? Yes, it is. It's constant pressure. That means it's an isobaric process. Okay, that's something to know about it. So now, is there a change in thermal energy? Now remember that this is a change in temperature. The best way to think about this is to think about isotherms. Remember that isotherms look like these 1 over x sort of lines, these hyperbolic lines. And so each of these points lie on a different isotherm, and the farther you get from the origin here is a higher temperature. So the final temperature is larger than the initial temperature. That means that our thermal energy must have increased. The next question is the work done, and this is really good to do on a PV diagram, and remember that we need to do the integral. Remember that work is equal to the negative integral of PdV. We can see that this would be a simple integral to do, but this integral is going to be positive since we start here and go this way. So while the integral itself is positive, that means that work is negative. So now look at the situation. We need to have an increase in thermal energy, but our work is negative. So what can we say about Q? We can try to determine its sign, we can try to determine if it's zero, and we can try to determine how the magnitude relates to work. So go ahead, pause the video, and think about this on your own. Q must be positive in this case, and the magnitude of Q actually must be larger than the magnitude of W. And the reason for that is, again, the sum of these is your change in thermal energy. We need a positive change in thermal energy. We need an increase. But work would be a decrease in thermal energy. So we must have enough Q to cancel out the decrease from work and give us the appropriate increase. So Q must be positive and larger in magnitude and work so that we get a positive change in thermal energy. And again, this last step we would only be able to figure out from the first law of thermodynamics, though these first three questions we could have figured out simply from the PV diagram and knowing about ideal gases.